All right, great. Well, let's get started. All right, so can everyone hear me? This is all right? Yeah, great, perfect. All right, well, my name is Erik Osheim, and my talk today is about intervals and interval arithmetic. So the title of my talk is that intervals are unifying uncertainty, ranges, and loops. There's a bit more to it than that, but that's sort of the big idea. So first I should just briefly introduce myself. I'm a member of Type Level. I'm one of the maintainers of Spire, along with Tom Switzer, who's also here. And I like to say this as that I have a sort of a dual interest in expressiveness and performance. I would say this talk is almost more about expressiveness, but I try and keep both in mind. I feel like both are important. And I do a lot of data science and sort of data janitorial work at meetups, so that we're using some of this stuff there. I don't know if we're using intervals specifically, but we use Spire. And if you want to look at some code that I've written, you can check out my GitHub page here. Great, so just to get started, I try and make sure all my slides are runnable, Scala code, at least the ones that are Scala code. So you should just assume that these three imports are happening. This basically brings all the types, all the type classes, all the implicit operators, just like the works. And it's really handy for playing around and just seeing all the different stuff you can do. And you can find the code for Spire in the Spire repo. So what will this talk cover? Well, so first I want to give a basic description of the interval type and kind of more just like what intervals are, not just in Scala, but like in the world, you know. And then talk about interval arithmetic, uncertainty, error propagation a little bit. And then kind of talk about set operations on intervals, thinking about them as sets and iteration more generally. There'll be like a little demo. I actually left my real demo on my other pants or other computer, so to speak. So I have like a sort of smaller demo than I was planning, but it'll still be cool. And then a conclusion. Intervals. And so some of you, who is like an engineer who has studied intervals or interval arithmetic like for real? So like a few people. So the early part of this talk might be less interesting to you all, but hopefully the implementation will be interesting. The rest of you are going to hopefully learn what this stuff is early on. So the definition we're going to kind of go with for now is that intervals represent a range of real numbers. So you might say all numbers between 3 and 6. And so already this probably sounds pretty familiar because Scala actually kind of has a DSL to express this idea in some sense, which is scala.range. So we've got two different ranges here on the board. You can see one of them is inclusive using 2 and one of them is exclusive using until. So those sort of seem like they fit the bill, you know, all the numbers between 3 and 6. And like I said, there's two modes. Both cases include 3. There's really not a good way to like exclude 3 from your Scala range, which there's sort of an asymmetry there that's maybe a little bit displeasing. I guess the real question is, do you think that all the numbers between 3 and 6 should include 3 and 6 or not? Like, what do you think, intuition-wise? Who says it should include it? Okay, so we got Dick maybe saying no. Okay, well, let's not do a poll. It's fine. Anyway, I'm sort of going to argue that actually range is not really the right abstraction. There's a lot of reasons, but maybe just the fact that the first is always inclusive is like a clue that it's not really going to work. And just to take a step back, I mean, there's in math class or various places you might use intervals, there's a sort of established notation which I'm going to use throughout the talk. The thing that's a little bit weird about it is that it sort of conflicts with notation in Scala. So like that 3, 6 isn't a tuple. In the context of intervals, I want you to think about that as sort of an interval between 3 and 6, but excluding the endpoints. It's exclusive. So it doesn't have 3, it doesn't have 6, but it has everything in between. I'm going to try and be clear on which stuff is Scala syntax and which stuff is math notation, but I do think that this notation is really helpful to talk about this stuff. It's way less cumbersome. So square brackets are inclusive, so the Scala range with 2 is pretty much what you get. And we can combine these, so you can have one side be closed and one side be open. One side be inclusive and one side be exclusive. And there's also some special cases that are intervals that I just want to introduce the notation so you can kind of understand them. So we got the empty interval, doesn't contain anything, empty. And then single values, we can kind of treat them as like degenerate intervals. There's, you know, it's an interval that only has one thing in it, basically. And then there's these other interesting intervals that have the infinity symbol. And infinity is not a number, right? We all know that. But we can sort of think of it as like a limit or a bound. So when we use infinity, we're basically saying that there is no bound on this side. You know, it goes from 3 on up towards infinity, or from 0 down towards infinity, or it's just everything. And those are called unbounded intervals. So anyway, going back to range, there's like a weird sort of thing, and this is kind of an intuition that I want to get at, which is that someone already alluded to the fact that Scala collections have a contains that's sort of bogus, right? I think most of us can agree that Scala contains is sometimes bogus. And you can see here that it returns false for 4.5, and that's definitely not what we would want. I mean, like, we might want it to be a type error, but if it type checks, we definitely want this to be true. I mean, for the definition of an interval, I'm not saying range is wrong to have this behavior, just that range is an unsuitable interval for this reason. The interval from 3 to 6 should contain 4.5. And you know, one of the reasons for that is range was written just to support int. I mean, it's very limited. And I'm sort of picking on range. Like, I feel a little bit bad about this. You know, it's like sort of kicking someone while they're down a little bit. Range is fine. It's just not very general. Like, it only does one thing, and it doesn't do the thing that I'm talking about here. And let's skip numeric range for a minute. Pretend like that doesn't exist. So the goal for our implementation in Spire is to support any numeric type you want. Not just, we're not going to settle on one and then force you to live with the consequences. We want it to work for everything. So it could work for int or double or anything that it basically is a number. There's sort of another problem, another reason why range isn't very good, and that's actually that, like I said, intervals have to be all the real numbers between two bounds. I don't really want to get into too much what uncountable means, but it means not only is there an infinite number of them, but like you could never possibly hit all of them using like an algorithm that we would write. So basically, what I'm saying is you shouldn't have a size method or a length method. That just doesn't make any sense for an interval. Like, it couldn't possibly do anything. And so since all Scala collections pretty much have to have this stuff and kind of assume that you can like iterate through and hit all the values and sort of assume that you can call length on it, like we just shouldn't think of this as a collection. I mean, maybe intuitively it seems like a collection, but I'm just arguing that that's the wrong intuition. So yeah, design goals should be defined in terms of these endpoints, not a container. Should support the unbounded intervals. That's just because I think they're cool and we should support them. And I want it to be generic. I want to parameterize the number type. I think maybe some of you have heard this idea of intentional definitions versus extensional in terms of like sets or something. And so what we're talking about here is an intentional definition. We want to describe an interval in terms of like the constraints that values must fulfill to be in the interval. We don't really want to like list all the values out on a piece of paper because we do that forever. Everyone kind of with me so far? Is this all making sense? Yeah, mostly? Okay. You should feel free to please, like if you get confused or you think, even if you're not confused, if you think I'm saying something confusing, please feel free to stop me or ask a question. But anyway, moving on. Let's say that we're representing this open interval xy as an interval of type A. So what is the thing that we really know? Well, according to the way intervals get talked about, we know that x is less than y. If they were equal, we wouldn't use this notation. We'd use that point notation that I showed you. So we can sort of assume that this is like an invariant that all intervals have to obey. You know, with the understanding that like infinity is not really a value, but maybe it sort of, you know, negative infinity in some sense is less than all other values, so that kind of fits. But we definitely need to be able to compare these A values to know, you know, if our interval is valid or how, you know, which numbers are bigger or less than our endpoints. And so in Spire, we would use an order to do this. You know, in Scala, you might use ordering. Scala Z, I think, has like, I forget what they call it, if they call it ordering or order, or you know, something like that. It's the same idea. We just need to be able to take any two A values and know if they're equal or if one's less than the other. Great, so that's pretty much, we're going to go straight into interval arithmetic, because this is what makes intervals cool. I mean, intervals, right now they maybe seem like a glorified predicate or a glorified type of set or something, but actually they're pretty awesome. So why bother creating intervals at all? And so a big reason, like I think, you know, the reason that this stuff got started maybe in the 50s or 60s was for uncertainty about values in engineering. So you would say, you know, we have something that's like 3, but there's an error tolerance, like plus or minus, you know, some error threshold. Like our machine is supposed to cut things at, you know, 2 meters, but you know, there's a little bit of wiggle, so maybe we have to take into account the fact that it might be off by a few millimeters or something. And so that's kind of where you get this idea of error tolerances, and those can be thought of as intervals. You can also use it to work with a set of values efficiently. That's another thing. And there's sort of other stuff, which is that sometimes you have a problem that's very hard to answer exactly, but you can kind of put, you have like upper bounds and lower bounds where you know stuff is. And so sometimes if you just do the math with these intervals, you find you don't need to know exactly. You can say, oh, well, we can skip the hard work of determining exactly what's going on by just using an interval and seeing if the whole interval happens to be like above or below some value or something like that. Or we can prove that two things couldn't possibly be equal, then we don't really have to do the hard work. Finally, this is something I'm not really going to get into, but there's a bunch of stuff out there about how certain kinds of distributed calculation really take advantage of intervals where due to the fact that stuff's being evaluated in different orders, it can be hard to unify the values you get at the end. So if you don't have intervals, you kind of have to start over if you hit these conflicts. But with interval arithmetic, there's a way to kind of incorporate all the different inputs from different workers to create an interval output that ends up being really efficient, apparently. That's something, if you're interested in, you could investigate more. So how do we use intervals to do arithmetic? The mathematical intuition here, even though intervals have an infinite number of stuff in them, this is math, so we can deal with infinity. So the idea is you would just do the operations for all the individual elements and then basically build the interval that contains all the results. So for this example here, I've got the interval 1 to 2 with containing both 1 and 2, and I'm going to add 1 to it. And what that really means is that if you imagine kind of like all the values in that are going to have 1 added to them, it sort of shifts the interval down. So from 1, 2, it goes to 2, 3, basically. Does that sort of make sense to people? I've got like a nice little ASCII art diagram here that kind of shows you, like, there's a number line up there, and you can kind of see that we've got an interval from 1 to 2 and a point, and we add the point, and then kind of shifts the interval over. Hopefully it's not super confusing. But, right, so I think this is a really, if you find yourself being confused about why interval arithmetic is producing a result, I think thinking about this in terms of these number lines is really helpful, where you can sort of say, oh, well, what value could I take from the first and take from the second to get some value in the output interval? Because that's really all the output is just all the possible things you could get given the inputs. And so as you can see here, we don't just have to add constants, we can actually add two intervals the same way. So here's, from 1 to 2, from 1 to 3, you add them. The smallest value you could get is if you take 1 from both, you'd get 2. The largest you could get is if you took 2 and 3, you'd get 5. And then just, using some common sense, you can kind of see that everything else is in between. That's the way you do it. And so even though we have an infinite set of values, we don't really do an infinite amount of work. We know that because of the structure of the interval, we know that if we just handle these endpoints, in this case, that's all we really need to do. We add the lower endpoints, add the uppers, and you're done. Some of the other operations actually are a little bit harder than that, but that's kind of the idea, is you just sort of, rather than doing an infinite amount of work over, or doing a work over a really large collection, we're just figuring out kind of logically what are the possible things that could happen, and then you just check those, and then be done. So I say that it generalizes because there's other operations, like multiplication and stuff. And so basically, we need what I'm just going to kind of hand-wavingly call well-behaved operations. So obviously, we need the operation to be deterministic. I mean, let's say that you had a random function that could do anything, then I don't even really know how you would model that, because who knows which value in the middle would get hit by some random branch and produce some output. You couldn't really produce a deterministic interval as an output. So interval operations like this shouldn't really rely on mutable state or on non-deterministic effects, I don't think. You could maybe argue with me about that depending on what kind of non-determinism you're talking about, but in general, I don't really think it would work. And basically, to be more specific, I think what you really want is you'd like the range of outputs to be determined just by the endpoints and 0, and like maybe a few other points that are known ahead of time. So a lot of times, you can just check a few cases and then get a result. We sort of need to be able to do that. And finally, you just need to know what to do in the unbound case. So if we have like an interval that contains everything, that doesn't actually have specific endpoints. So what do you do? And usually there's a pretty obvious thing to do, but I just mentioned it because you could imagine a function where it wouldn't really work. And so Spire's interval right now supports all of these functions I put at the bottom. So absolute value, min and max. You can ignore why there's a v on the front for now. And then plus, minus, times, divide, reciprocal, powers, square roots, and n roots. So a lot of stuff you might do with numbers. Not everything. Like we don't support sine right now. We sort of could actually. That would be fine, but we just don't. And so let's jump to actually what the Spire code would look like. So this is some code that just builds 4 different intervals using kind of 4 different ways of constructing intervals. These are all going to be intervals of doubles. And I've shown you what the sort of 2-string output of those intervals is on the right in comments. But there's 4 different ways of specifying it. So as you can see, in one case, we just provide the bounds, and by default, it gives us a closed interval. We can ask for a specific point. We can use this interesting sort of error threshold plus or minus operator. Or you can just basically say, give me everything above some value, which gives us the interval from above 0 towards positive infinity. And so then there's just some simple stuff we can do, like checking to see what's going on, which points are inside, if it's empty or not, and so on. And then here's some actual real interval arithmetic going on. So I put the definitions. This is the same values as the last slide, but I just put them here so you can kind of remind yourself. And then I'm just going to take a moment to kind of walk through some of these to kind of try and motivate why we got the result we did. I think the first one's pretty straightforward. If you look at W, we get W times X by just multiplying both bounds by 2. That's pretty straightforward. 3 goes to 6, 5 goes to 10. Everything in the middle goes to the middle of the output. And then we can take that result and we can shift it by another interval. So by Y, you see that it introduces that little 0.1 error threshold where it goes from 15.9 to 20.1. And so I think a lot of the engineering applications of intervals are going to be more like values more like Y, where you're going to have like a larger value with some small error tolerance, but those error tolerances might add up like when you multiply or do stuff. And so this gives you a way to track that through larger calculations. Like these calculations are still pretty simple, but it could be arbitrarily complicated, right? It could have lots of stuff. And then, as you can see, we can take the minimum of 2 different intervals. So Z is this interval that shoots off to infinity, whereas X times Y obviously doesn't shoot off to infinity, but you can see that we take the minimum value of those intervals, and what we end up with is we know the value is going to be greater than 0, because neither of those intervals contains 0 or anything below it. And we know that the highest possible value it could be would be 20.2. It couldn't be larger than that because if, as you can see, X times Y's upper bound is 20.2. So if Z is somewhere up towards infinity, we just ignore it and take the smaller value. That's kind of how this works. You imagine all the cases on one side and on the other and come up with a result. And so finally, here's sort of a more interesting looking calculation where you could imagine like if Y is the side of a triangle, we're calculating the hypotenuse basically of like a right triangle where the two sides are the same length. So we're y squared plus y squared, take the square root of that, and that's going to give you the length of the hypotenuse. So we can see that if we wanted a triangle whose sides were exactly 10 units, but there's this error threshold in our machinery, the hypotenuse, the sort of smallest it could be is this number, and then the largest is that. So there's maybe like a 0.28 unit slippage there that we have to, our customers might experience that. That's like an example of what it might look like. Do people kind of follow this? I feel like this is hopefully still pretty straightforward, but definitely let me know if you're confused or something. And so actually, even though I just said that intervals are real numbers, and I sort of reified that, now I'm kind of saying that Speyer's intervals actually work for anything with an order. So we can make an interval of strings. So this is all the strings that are lexicographically between bats and cats, including the endpoints. So cats with a Z would not fit, but batter does. We can also create intervals of option integers. If for some reason you wanted that, I kind of don't know why you would, but you could. And we can have empty intervals as well. So there's an empty interval of list longs, because it is possible for us to order list longs. And so, as I said, you're probably like, why would you do that, or why is that even allowed? Shouldn't everything have to be a number? And the answer is that basically, the way we handle this is rather than restricting interval creation to requiring like a field or some like really heavyweight, powerful type class, what we choose to do instead is let you build the interval right off the bat, but we don't give you access to the capabilities unless you have the type class in hand that works. So, you can't, unless you have a way to add intervals like some kind of semi-group or monoid or something, we wouldn't let you add them. But we would let you create the interval, and you could then test to see if stuff's in it or not. Similarly, if you want to multiply, you need something more powerful, take square roots, and same thing. So as you can see, none of these things compile. Like you'd get an error. And to be clear, the things that you would need to see kind of tell you what capabilities you need. So hopefully you all have sort of been exposed to type classes. I'm not really going to explain. If you haven't ever used type classes in Scala, then I apologize, but I'm kind of just going to assume that you understand the idea because it's been sort of around for a bit. Feel free to come talk to me after the talk if you're confused about it and want some help with it. But the idea is, for this purpose, type classes are really capabilities. I think that's how you should think about them in general, is if we have a generic type, we want it to be able to do some stuff, the type class provides those capabilities. So in this case, if we want to multiply intervals, the capability we need is a semi-ring. We need the properties that a semi-ring has. If we want to take the square root, we need it to both have a ring and an n-root instance. And if we want to do division, we need a field instance. So the compiler will tell you that your type doesn't have those things. And maybe if you think we left them out because we were just lazy, you could implement them yourself. But maybe you would find that you actually can't implement them because the type just doesn't work that way. And that's what functional programming is all about, basically. So so we've got interval arithmetic done. Now we're going to jump and talk about intervals as specialized sets, because that's like another interesting use of them. And so I showed you how to combine intervals using arithmetic, but you can also think about them as sets. In fact, maybe it's more natural to think about them that way. So as I've shown you, I've created some intervals here, and we can obviously do contains tests on them. But we can also do a whole bunch of other stuff too, which is kind of neat. And most of these operations only require the order, so they don't require like rings or fields or that kind of stuff. So you could use a string, use it with an interval of strings or what have you. So we've got like an intersection, like a union. We can test to see if intervals intersect. So that's often really useful. Like if you have two sides of an equation that are supposed to be equal, a thing you can do is you can evaluate them with intervals and then see if the solutions intersect. And if they intersect, that means that they could possibly be equal. You haven't proven that they are equal, but you've at least proven that it's plausible. If they don't intersect, you can be sure that they're not equal. There's no chance, right? Those intervals are disjoint. And we can also take like the opposite, or like the complement of an interval. So if p is an interval, tilde p there kind of means give me the intervals that contain all the numbers not in p. And so you can see that instead of producing one interval, it produces a list because you might take a chunk out of the middle of the number line, but you need the bottom of the number line and the top, and that ends up being two intervals rather than one. So, I mean, you're never really going to get more than two intervals, but list was just like a sort of a convenient type to return. And you might actually get nothing. So, for example, if you have the interval that's all numbers, you complement that, there's no intervals you're getting back. So rather than give you an empty interval, we just give you nothing, because that's, in some sense, like just as correct. And here's sort of a visualization of that. Again, another one of these great ASCII art diagrams that you've probably come to love or hate. So basically, as you can see, when we take like the complement of t down at the bottom, we're taking a byte out of the middle of this number line. In other words, it goes off towards negative infinity, it goes off towards positive infinity, but there's this little byte eaten out. And you'll also notice that t included its endpoints, which means that its complements don't include their endpoints, right? T claimed those endpoints, and so when you take the complement, you have to exclude them. One of the things, if you implement interval arithmetic yourself, you're going to find you spend a lot of time losing sleep over how the bounds end up. Like if you've got what kind of bounds here, then what kind of bounds do you generate on these new intervals? That ends up being very important, obviously, to do this stuff correctly. And as you can see, we can intersect two unbounded intervals to get a bounded one, because each interval constrains one side. But if we union them, then we just get the whole number line, because one of them provides all the negative numbers, and one provides all the positive. Again, is this kind of making sense? Yeah? Awesome. So then, you might be like, I really wanted something that's even more like a set. Like those lists bum me out. I just want a single type that I can treat like a set, and maybe there's two intervals, but I don't really care. That would be awesome. And in fact, if that's what you want, then Rudiger Clan, at least I hope that's how he says his name, but he's got you covered. He's got like a really nice immutable interval set implementation that efficiently stores sort of like the various endpoints of a set of intervals, basically. So you can do this kind of stuff. You can also get Spire intervals out of it if you want. I think it's got good Spire interops. So I definitely encourage you to check out interval set if this is something you're interested in. And we might try to include it in Spire or possibly like a contrib module or something else. Definitely recommended. So some of you maybe are worried now that I'm talking about mapping over sets, but the question is, can you map over intervals? If it's sort of like a set, can you map over it? And the answer is you sort of can. You can map over the endpoints. So here's like an obvious method that we could write that does it. Great. And you might be like, well, why did you call it map bounds? It's stupid to make up this name. We could call it maps perfectly good. Well, I didn't really want to call it map because it's not really a map. It doesn't really behave like map, and if you use it like map, you're probably going to get burned. So, if you were like an enterprising functional programmer, you're like, great, let's use as few abstractions as possible. Like you saw Runar's talk, and you're like, yeah, I'm going to do it. And so you decide to implement, rather than use the built-in arithmetic stuff that I wrote, you're like, I'm just going to do it all with map bounds. Map bounds is like super general. Let's just use that. And you're going to find yourself in a world of pain, basically. Because as you can see, all these functions that you might wish you could just use map bounds for actually return very different intervals. And the reason for that is that you can't just consider the endpoints when you're doing intervals. You really have to consider the zero and kind of how the signs are affected and whether things are getting reversed or not. So like, just to look at the first example, when we square this interval from -2 to 2, you and I, looking at it, we can say that, well, if you square -2, you get 4. If you square 2, you get 4. But if you square 0, you get 0. So 0 is clearly like, it's got to be at least as low as 0. And so it turns out that 0 to 4 is the correct interval for that. But if you do only the endpoints, you'd say, well, -2 squared is 4, 2 squared is 4, 4 to 4 looks good, right? Done. And that's just, that's probably not what you want. I mean, that's certainly not like valid interval arithmetic. And similarly with negation, you might wonder what's going on here. What's happening is that map bounds is negating the endpoints, and now the lower bound is greater than the upper bound. And just according to the definitions of the way intervals work, that's empty. I mean, it can't contain any values, and so then you get the empty interval when in fact, you probably wanted the same interval you started with in this case. I mean, negating -2, negating 2, you essentially just flip the endpoints. So map bounds doesn't really work, and you might be asking yourself, well, what can we do, like fix it? Can we make map bounds like consider, like a 0 and do some other stuff? And like, sure, maybe you could, I don't know. I didn't really think that was a good plan, so there's maybe a better way. So I'm gonna introduce polynomials. I'm just springing it on you. This talk didn't have it in the summary, but here we go. So polynomials are basically functions of a single variable with like a limited set of operations. So it's not like a function that can do anything. It's a function that can only do certain specific things. Sort of like the stuff you might have done in like high school algebra or something like that. So anyway, here's some polynomials that I wrote out. They're functions in terms of x. And that's obviously not valid Scala code. That's more like sort of math notation that I'm using just to kind of show you. So as you can see, they just take x and they do math stuff to it. Like they take powers of x, they add multiply by scalars, add other values, and so on. And so Spire has support for polynomials, which is very cool, and we can use that in a couple different ways here. So there's this fancy string interpolation, which is kind of the easiest way to use it, but it's like a little bit ad hoc. I mean, if you want a polynomial of rational numbers, I think it's like by far the most readable, but there's also these two other ways you can build polynomials if you want as well. And basically the idea is you're basically saying for each power of x, what's the coefficient for that power? And polynomial is generic, so the coefficients can be long or double or rational or whatever you want. Anyway, and thanks to James Thompson for providing polynomials. So what we can do here is basically translate our interval through the polynomial. And because of the structure of the polynomial, we know that the polynomial is well behaved, therefore we can be sure that the intervals we get out are correct. So in terms of the stuff we were trying to do with like -x, when we translate through the polynomial, we get the right result. And we can be sure that translate will preserve the interval correctly. So that's pretty great. I gotta rush to save some time. But I was going to show you how this works. Maybe we're going to skip it, actually. I'm kind of low on time. But it's like a pretty simple implementation for what it does, actually. The idea is basically you turn a polynomial a into a polynomial of interval a, and then you just evaluate the polynomial. So pretty elegant. Intervals as souped up ranges in 2 minutes. All right. So basically, we can think about what Scala uses as range, and we can talk about the same intervals. So we can construct intervals corresponding to Scala's ranges. I say this again, but basically if you're looping over ints, you probably shouldn't do this. It's not going to be as fast. But there's a bunch of advantages over like numeric range, which is that you don't need to specify a step. Intervals are perfectly happy to just talk about a range, and you can, once you decide what the step is later, you can use it, but you can still do other stuff with it. Contains checks are very fast, much faster than looking through a collection. You can do math operations. There's overflow checking, so if you're using like double or int or long for some reason, you don't have to worry about running off the top with like a large step. And you can write infinite loops if you want. Great. So anyway, so here's some folding and iteration. So we've got an interval, we can fold over it, which ends up looking a lot like fold left on a range. We can also just build iterators, do the same kind of thing, and we can write this loop that takes a step by 25 and prints all the stuff. So kind of a gee whiz, but it's interesting. But there's some fancier stuff we can do. So if you want to, you can express your loop conditions as intervals, then you can union them or intersect them or whatever, and that might be, for you, that might be a nice way to do it. Here's like a method that I think lots of people want, but don't actually ever implement correctly, which is dividing sort of you've got an integer number of steps, like say like 100 or something, but you want to divide it by some weird number, and you want to be sure that the buckets are all the same size, and you don't really want floating point error, like you really want the ends to be right. And there's a really nice way to do this with Spire. So this is a problem you've had. As you can see, like even with a divisor of 7, it like pretty much hits all the stuff correctly, and at 3. And you've got infinite loops. Great. So there was going to be a cool demo, but I'm like literally running out of time. So caveats, don't use this with ints if you want it to be really fast. It's not specialized. And there's a couple other problems, like your order needs to obey some extra laws when working with rings. And there's a few rounding issues with double that come see me if you want to know about them. There's a few more slides, but that's it. So anyway, hope this was interesting. Maybe encourage you to check this stuff out, and feel free to talk to me about it if you're interested. Thanks.